All right, guys, we're going to talk a little bit about acids and bases. In biotechnology, for those of you continuing, the acidity or alkalinity of a substance changes the shape or the conformation of proteins, if you can remember that from biology. So we're really concerned because enzymes, we use enzymes to do the work of biotechnology, and enzymes are proteins. So we want to make sure that we have pH correctly. So some of the chemistry classes aren't doing that this year, but we have to. So let's get through it. So acids and bases. So there are three main definitions for acids and bases, right? Right. So there's the Arrhenius definition. So Arrhenius, let me make this a little bigger. So Arrhenius says that acids donate hydrogen ions, and bases donate hydroxide ions, right? So if you think about things, right, when you're reading substances, if the substance starts with an H, it's most likely an acid, right? So, and then we have things like this. Is it an acid? Well, we'll find out. All right, so whether water is or not, we'll leave to a different time here. But we know these two are acids because they're leading with an H, right? So acids donate. So nitric acid, HNO3, we know it's an acid because it leads, and it will donate. It will donate that hydrogen ion, right? Sodium hydroxide, right? So this led with an H. It ends with an OH. So we know it will donate a hydroxide, it'll be a base. All right, so that one's pretty easy. So that definition doesn't fit everything. Okay, so since that definition doesn't fit everything, let me make this a little smaller here so it all fits. All right, so we BronstedLowry. Two other guys came up with a different definition, and they said an acid. Let me make this so small. An acid is a proton donor. Well, what's a proton? A proton is a hydrogen ion. So they really didn't say anything different than what Arrhenius said, because it still donates a hydrogen ion. So an acid's a proton donor, right? And a base then becomes a proton acceptor, right? So in this we have H3O, right? And we have OH. So if we look at it, H3O is hydronium, and then we have hydroxide. So according to Arrhenius, if we look at the bottom example, we have H3O again, or hydronium, and now we have ammonia. So ammonia, since it has that extra pair of electrons, it can accept a proton, right? And then because of that reason, it's an Arrhenius base, or a BronstedLowry base. So things to remember is this base right here. So this essentially is any anion can be a BronstedLowry base. And then any molecule with unshared pairs. Right? So any of those, right, can be bases, right? Any anion and any molecule with unshared pairs. So if you think about water, water could also be a BronstedLowry base. For BronstedLowry acids, right, we can also talk about things as far as how many hydrogens they could donate. So for instance, this right here we would call monoprotic, because it can donate one hydrogen. This right here we would call diprotic, because it can donate 2, and this would be triprotic, because it can donate 3. All right. Another aspect of Bronsted-Lowry is that every acid has a conjugate base, and every base has a conjugate acid. All right, so if we move this down a little bit, if we see here in this example, right, I've got water and I've got bicarbonate. So bicarbonate it leads with a hydrogen, but notice it's got a negative sign here. So it's an anion, so by definition it's a Bronsted-Lowry base. Right, water, since it leads with an H, can be an acid. It also has an extra unshared pair of electrons, so it can be a base as well. But at that point, it's working as an acid. So since water donates its hydrogen, right, it forms hydroxide. So hydroxide is its conjugate base. Right? Bicarbonate accepts a hydrogen, so carbonic acid would be its conjugate acid. Something to think about. I'm going to erase some stuff here. Because I need some room. Alright, something to think about is this water is a weak acid. Essentially water is neutral. If that's a weak acid, this is a strong base. So this is a moderate base. So this is a moderate acid. If I have a strong base, it will make a weak acid. If I have a strong acid, it'll make a weak base. Okay, so those are conjugate acid-base pairs, right, down here. All right, moving on. So because it's not confusing enough, we have Lewis acids and bases. So remember, Lewis is that dot guy, and those dots are electrons. Let me expand this a little bit. Oops, I didn't mean to move that, but I just meant to make it bigger. Okay, there we go. So Lewis acids and bases. So remember, in Lewis's world, dots are electrons. So a Lewis acid, right, is an electron acceptor, right, and a base is an electron donor. Okay, so if we look at this, first we have bromic acid, right, and we have methanol, right. So in this instance, bromic acid is going to donate the H, right? So it's essentially a Bronsted-Lowry acid, so it donates an H+. Now, the hydrogen ion can accept an electron pair, so it becomes a Lewis acid, right? The Lewis base is an electron pair donor. So if you notice that this has extra pair of electrons. So that extra pair of electrons I can't get my pen. There you go. So my extra electrons were able to bind with that hydrogen ion, and that's what makes it a Lewis base. Okay, so you don't need to worry too much more about that. All right, so naming acids and bases, that's the next thing. There's some easy rules, right? So it depends on the suffix of the anion, right? If we look at HCl, you would say hydrogen chloride, right? But since it leads with an H, it's an acid, right? So Cl minus is chloride. So since it's an ide, it gets the prefix hydro, and then ide becomes ic, and it ends in acid. So HCl is hydrochloric acid. Right? So this is called a binary acid. So binary means having only two types of ions, right? It has the hydrogen ion and the chloride ion. So binaries always start with hydro, right? The ide becomes ic, and it ends in acid. So these here, eights and ites, these are your polyatomics, right? So if we have this, so this right here is sulfate, right? Right, so sulfate, so 8 becomes ic, so you would call this sulfuric acid, right? If I had this, right? So this is sulfite, right? So ite becomes us, so this would be sulfurous. Sulfurous acid. If I did this, right? So remember now this is sulfide, right? So this would be hydro. Hydrosulfuric acid, because this is a binary, right? So this one right here is also a binary. So all binaries start with hydro. These two in the middle were polyatomic anions, so they don't get the hydro. They just get the ic and the s. All right, so that's naming. I just want to introduce you to it. Next thing we need to talk about is the ionization of water. So water self-ionizes. So if we have, I'll use black. So if we have water, right, I'll draw both arrows because it's a reversible reaction. I get hydronium plus hydroxide, right? So hydronium would be the conjugate acid, and hydroxide would be the conjugate base. The KEQ, remember the KEQ for that reaction, would be the products over the reactants. Okay, but we're not interested in the KEQ. We're interested in what's called the ion product. So this right here is the ion product. Right? So the KW is simply the top part. Right? And the constant for that, and I put it up here, it's up here at the top, is 1 times 10 to the negative 14. For water, it's always 1 times 10 to the negative 14. For anything in an aqueous reaction, or an aqueous environment, it's always 1 times 10 to the negative 14. Right? So, if we think about it, right, I'm running out of room here, so let me find some more room. I'm going to erase the stuff on top here. Okay, so KW then equals ion squared, because the ionization reaction forms an equal amount an equal amount of hydronium and hydroxide. So if you think about this, so ion equals the square root of 1 times 10 to the negative 14, right? And the square root of 10 to the negative 14 is 1 times 10 to the negative 7. So that's when we see that right there, right? So in water, in pure water, it's always forming ions, and the amount of hydronium it forms is 1 times 10 to the negative 7. The amount of hydroxide it forms is 1 times 10 to the negative 7. So the ion product, or the Kw, is always 1 times 10 to the negative 14. Okay, so that's a constant. If you just remember this number right here, right, then you'll always be fine. So you probably remember the pH scale from biology, right? So the pH scale says that acidic is 0, so acidic is actually 0 to less than 7, right? And alkaline is greater than 7 to 14. So for pH, this would be most acidic. And 14 would be most basic. Okay, so most acidic and most basic. All right, and then 7 we know is neutral. Right? If on a test or quiz you say that acid is 0 to 6, is probably incorrect, because 7 is neutral. So 0 to less than 7, 6.9999999 is not neutral, right? It's slightly acidic. So 6 would be a weak acid, and 0 would be a strong acid. 8 would be a weak base, and 14 would be a strong base. All right, so here's some common equations you'll need, right? So pH plus POH is 14. So pH right here, we'll talk about, is the negative log of the hydrogen or the hydronium ion, right? So if my hydrogen is equal to 1 times 10 to the negative 7, then pH is equal to negative log negative 7, which is equal to pH. Oops, I'll just do this. Which is equal to 7. Right, so if you type that into your calculator, right, you'll do the negative sign, the log function will give you parentheses, you put 1 times 10 to the negative 7, right, or use the 10 to the x and type in negative 7 for the x, and it equals, and it will give you 7, right? So, because what a log is a base 10 system, and it rationalizes the exponent. So if you think about this, right, so pH makes the exponent a real number. So negative 7 times negative is equal to 7. Okay, so that's how it works, right? POH would be the negative log of hydroxide, right? So POH is negative log of hydroxide. So if I did POH is 1 times 10 to the negative 7, I'd get 7 plus 7 is equal to 14. Okay, so not really that tough. If you look at our pH scale here, right? So if our pH is 0, look at the top, then I have 10 to the 0, which is 1, which means it's 100% hydrogen, right? And then my OH would be 10 to the negative 14. So 0 plus 14 would be 14. The pH was 1, I'd have 10 to the negative 1 times 10 to the negative 13. I get a pH of 13. right? So that's basically how that works, right? And the pH of 1 plus the pH of 13 is equal to 14. So you can go all on down these. You could add the pHs and the pOHs. You get 14 every time. You could add the hydrogen, or you can multiply the hydrogens times the hydroxide concentrations. You would always get 1 times 10 to the negative 14. Okay? So what if pH isn't that simple, right? So if we look here, we'll give you some more pH examples. So if I say what is pH? Oops, I didn't need to make it. What is pH? Right? So I could do that, right? Or I could say okay. Or I could say or I could say that. Right? So you could do either one in your calculator. You just have to type it in. I will pause it and I'll type it in my calculator. Let me just get rid of this. All right, so let me pause. Okay, so if you did these on your calculator and you typed them in, for the top you should have got 4.5, and for the bottom you should have got 4.3. So you can see that they're not necessarily the same thing. You'll have to type them in. If I ask you, if I said, what is the hydroxide, right? The concentration if the pH is 3. Well, we know that if pH is 3, then the pOH has to be equal to 11, because pH plus pOH has to equal 14. Then you would have to use your 10 to the x function. And x, for x, you would type in negative pH, right? Because we're kind of going backwards, right? So let's say maybe I set this up right here. All right, so what we would have to do here is we'd have to use the 10 to the x, and for x we would type in negative 5.3. So let me pause it. And I would get 5.0 times 10 to the negative 6. So if you type that in, you get that. And this right here now, right, is equal to my hydronium concentration. Okay, so that's probably enough for today. So I'll post a homework problem, and then if I think of anything else I need to think of, I'll post another video for you. Okay, so have a good night, and I hope you're all doing well, and I'll talk to you soon.